Hi, welcome once again to Baptronics Labs here in the mountains of Colorado. I'm Bruce, and today I'm going to be demoing a Hitachi V-1050F 100 megahertz dual trace, dual time base delay oscilloscope. Scope is in very nice looking condition. As you can see, and as you will see, she functions very, very well. Try and give you a little bit of a look underneath here if I can lift this thing up. And as you can see, the underside are rubber feet. And we are once again back in place. Okay, well, if you'll bear with me through the demo, we're going to do our best to demonstrate the DC balance on both channels A and B, whereby as you change your variable vertical gain switch through any of its divisions, you'll see that it doesn't jump around on the screen, that you remain level online. You don't get that jittery jumping. We're going to take you through all of the functions, the mode switch, the position controls, the intensity control, focus control, trace rotation, scale illumination. We'll take you through the time base, showing you an AC signal at 1 megahertz, and then we'll expand it times 10 to show you that that's working and that we cover the appropriate number of divisions. We'll take you through the various coupling, AC, DC, your triggers for auto, normal, the television. We will do a really interesting demo, I think, on the time delay portion of the scope, and we'll take a look at a video output signal from a DVD and use that time delay to examine a portion of the waveform that we pick on the top signal. We'll display an expanded version of it on the bottom. Virtually taking you through the majority of the function of the scope and showing you that it's working fine, calibrated, and demonstrating its use. It does get dry at times. When we go through the DC section where we demonstrate the reaction to DC signals on the screen, and the linearity, and the fact that we can, with precision signals, we can get exactly what we expect to see on the screen. That gets a little dry, but if you're interested in the scope and its performance, then you'd want to see that. And then we take you through the bandwidth test on the scope, so where we prove that the scope goes beyond 100 megahertz and lives up to its specs. So there's a lot to cover here. It can get a little dry. If you find it to be dry in a section, skip forward. I would recommend taking a look at the time delay section. I think that's a fascinating area. So bear with me, and we'll get going. Thank you. Well, I've taken the cover off of the V-1050F, the Hitachi, and I wanted to give you a look at the inside now that I've cleaned it up and checked a few of the components. It's nice looking. Complicated look to it. It's a 100 megahertz scope. Utilizes IC and discrete semiconductors. Looks in good shape, and so far everything I've checked out has been right on the money, so not worried about it. One of the nice things about the boards in this oscilloscope is that if you had to service them, they're serviceable. The boards can be removed easily enough, and the components are standard components that a person can grapple with, solder, and so on. So you've got a good chance of keeping this thing going if you ever did have a problem. But I'm going to prove to you that right now it doesn't have a problem. It performs very well. So stay with me, and we'll get a test going. Okay, here we can see that we have a nice 1 megahertz signal coming in into the scope and just being displayed. And as you can see, it's a nice sharp, maybe too bright. I can turn it down a little bit for the camera. But it's a nice sharp trace. Oh, wait a minute. Is it one trace or is it two? Maybe it's two. Oh, yeah, it is. Okay, so I knew it all along. Wanted to be able to demonstrate. And there we go. So one trace became two. Well, really the point to that is, in order for you to be able to have it look like one trace, then the gain adjustments had to be made right. Otherwise, you're on the same setting, you would not be getting the same gain. You'd have a little bit of flare out on either end, or maybe a lot. Depends. Okay, so that's good. Let's go ahead and take a look at channel A, and let's rotate through. So that's 5 volts per division, vertical gain. Here's 2, 1. Let's go ahead and move her down because we're playing with it. Approximately center right about there. Okay, here's 0.5, 0.2, 0.1. Really the point to this was to just show you that it was jitter free. And let's continue down. There's 0.5, 0.2 per division, 0.1. Very smooth transition. It's not jumping all over the place. And what I'm trying to point out there is that I've cleaned the switches. The contacts are nice and clean. Otherwise, you'd be getting very large amounts of jitteriness as you switch through. And the same thing goes for the variable volts per division. If I was to activate that, I can very nicely rotate through the change that would allow me to give. And again, the pots have been cleaned on that, so that's why it's able to do it. Okay, let's take a look at channel B. We have similar sort of thing. Here's 5 volts per division, 2, 1, 0.5, 0.2, 0.1. Again, very smooth transition, 50 millivolts, and so on. And if I activate the variable, same sort of smooth reaction, no jitteriness. So again, switches and pots have been cleaned on verticals and the adjustment, the variable adjustment for vertical. Let's move on from here. Okay, well, we got the scope on. Let's demonstrate the intensity control. Show you that it's working. Take it from full off, full brightness. We got plenty of brightness on this. Then back down to a reasonable amount. We have focus. Focus from an awful blur, and then blur in the other direction, and then down to the middle of the road here where we get nice sharp clarity. What about there? We have scale illumination, which isn't tremendous. Actually kind of hard to even see with the with the camera, but maybe you can see the difference as I rotate through it there. Scale illumination is working. Let's take a look at trace rotation. Easiest way to see that is to place myself in ground position on the inputs, and then go ahead and insert my screwdriver into the trace rotation, and then we adjust the rotation. So we see that we can do that. We can adjust the rotation, and then we bring her back in so that we're even horizontally to the line. Right about there. Okay, trace rotation's working. We have the horizontal positioning control. To the right, to the left, center it. Okay. My furnace is kicking on in the background, that's the noise, for those of you who wonder. Go ahead and put myself back on AC input. Looking at my 1 meg signal, I can go ahead and turn my horizontal frequency. Let's, right now we're set, and we'll adjust our positioning control so that we are exactly 1 cycle and 1 division on the screen. If I pull the times 10 magnification, I want to see if I have 1 cycle and 10 divisions on the screen. Turn up the illumination on the scale and hopefully we can see this. Okay, we start our trace right on the corner of the division here. We come 5 to the middle, and 5 to the right hand side, so we are exactly 10 divisions for a 1 megahertz input on the times 10 position right now, and if I push it back in, we will be 1 division in 1 cycle, or 1 cycle per division. So our horizontal is adjusted properly for 1 megahertz for the frequency, and our times 10 magnification is also proper. So that's been demonstrated. Let's move on. Okay, I have both A and B channels showing on the screen, and I am right now in the alternating mode on my switch. I could go to chop mode. Excuse me, that's additive. We're in chop mode here. Let's go to alternating. There's alternating. A little bit more brightness in the alternating right now for this 1 meg signal than what if I go to chop. And then we can go to additive and we add the 2 signals together. All those functions are working. There's channel 2, channel 1, 2, alt, chop, additive. So all of that's working. If I want to limit my input frequency to under 20 megahertz, I can push in this button here, and that will automatically reduce my bandwidth. I'd need to refer to a manual to figure out why I'd want to do that, but that's something that's there. And if I want to do a trigger view, let's say when I turn this thing on, I'm not sure where I'm at. I'm not seeing anything on the screen. I can do this trigger view. I can invert my channel. If I'm on B, I can invert B by a push of a button. So you can add A and B together and see them cancel perhaps. Okay, I've deliberately chosen different signal sources for A and B, and they're slightly off frequency, so you see B traveling. And the reason I'm doing this, I want to show that I can change my trigger source from A, which A is stable right now, to B, in which case B is stable, and now A is traveling. So my trigger source is working. There's also a line trigger and a external trigger, and those are available and working as well, but I don't have it set up to demonstrate, so we'll move on. Right now we are in auto mode for triggering. If I go to normal mode, then the only time I'm going to display is if I'm locked into trigger. If I turn my trigger off over here to the right, then we lose the screen. If I adjust it again to where it triggers again, you'll see her come back in. There we go. And then off and back again. In auto mode, I should be able to turn this thing and it won't make a difference. We'll lose lock, but we won't lose our trace. Okay, so both normal and auto are working. There's also a single trace mode that you can trigger manually by pushing the button. And a TV mode where we're locked into a horizontal frequency, I believe. 15 kilohertz, something like that. Anyway, most of the time you're going to be in auto, I would say, and you just choose your source for the trigger. Okay, we're going to move on. Alright, let's say we turned on a scope and things were out of whack. So let's put this out of whack. We're going to take our channel A vertical and we're going to raise it up off the screen. Channel B, we're going to take it off the screen. When we turn it on, we don't see a trace. Well, there is a beam finder button. It's right here. You can push that beam finder button, and no matter where the trace is, it'll bring it in onto the screen so you can see that it's there. Then you know you just got to make an adjustment to figure out what the heck's going on. So you may be off, if you're measuring DC in particular, you may be off the screen, and that'll help you find it again. Okay, beam finder. Okay, in this instance I've connected my scope probe to channel A, and then I'm connected to the 0.5 volt cowl. I've adjusted myself to 0.5 volts per division. I could choose a more higher resolution, so we're on 0.2 right now. We get 2.5 divisions, and I've had to adjust my my horizontal time-based control so that we could get a few of these square waves shown on the screen. And at this point you would calibrate your probe. Every probe has a calibration point on it. This one has it, this little hole where my thumb is pointing to right here. And I would put a screwdriver in that, and I would turn it, and you would see the bars on the upper and lower side begin to skew. What you want to do is you adjust it so that you get the straightest, squarest looking wave you can get. Then you've adjusted your probe properly. And the 0.5 volts is a calibration point. You can kind of check your calibration to make sure that you're properly calibrated vertically. And right now I am showing 2.2 up and, well, it's 1.2 up and down, a little bit over that. If I was to go another step, it'd be easier for me to see it. In this case, I'm 0.1 per division, so here's 0.1, 0.2, and 5 in between, so 2.5 divisions up, 2.5 divisions down. So I'm 0.5 in a square wave, which is what this thing says. Alright, so that's the calibration point. That's working. We'll move on. Okay, well, I've set the scope up in an XY condition. So we have a 1 megahertz signal coming in from my Hewlett-Packard 3320B, and we have a 1 megahertz signal coming in also from my Hewlett-Packard 8640B. And we have a Lissajous pattern slowly revolving, so we are just slightly off frequency between the two. If I wanted, I could adjust it to stand still, in which case I'd be equal in frequency. But as we can see, the XY is working great. That's really what I wanted to demonstrate. We'll move on. Okay, well, what I'm going to try and do now is to demonstrate the delayed time base. This would be time base B. And what it basically is used for is to allow you to zero in on a portion of a complex waveform and observe a secondary image underneath the image that you're working on that is expanded, an expanded image, and it's of the portion that you were looking at or that you're concentrating on. But it'll come easier if we give a little demo. Like right now, I have a complex waveform on my screen that's coming from a DVD player. And I have it coming in on channel 1. I'm in auto. I'm triggering off of channel 1. And I've adjusted for a static display as much as I can. Okay. So what I'm going to do is, first of all, I'm going to put my switch here into off of A and into intensity mode. And as soon as I did that, you'll see that everything brightened up on the screen. Okay. But now what I'm going to do, there is a little dial here called the delayed time multiplier. And if you watch on the left side of the screen, as I start to rotate this dial clockwise from 0, you're going to see the intensity start to diminish to where you don't even see hardly the image on the left. You see how I'm coming in on the left there, and I'm killing the brightness on the image, and the only thing that's bright is to the right of where I'm going. So let's say I'm interested in this portion right about there, but now I don't want to see all of this on the right. I'm more interested just in this slot right in here in the middle. So now what I do is I come over, and on my time base that I normally work with, which is the big black dial, I leave that alone. But there is a center dial that right now I have aligned with it, but I'm going to turn that center dial to the right. I'm going to increase this time speed on that. And what you're going to notice is I've now started blanking off on the right. So now my intensified area is zeroed in to a much smaller area. Okay, well, now I'm basically in that slot that I was looking at. Okay, so what does that do for me? Well, now I take this switch and I move it from intensified, I move it to alternating. And it's going to go from the intensified A display on the top, and it's going to show me the expanded high-speed B delay channel underneath. Because as you remember, I turned my dial up in increasing my frequency of sweep. And so what's going to be shown on channel B is something that is faster and expanded, but I'm showing it underneath A. Now if I rotate my little time multiplier, I'm going to take that little intensified area and I'm going to move it to the left. And as I move it to the left, I see that the B channel down below is moving also, and I get an idea. I can see what's going on the B, or I can see what's going on my complex waveform up here, intensified or expanded on channel B. So let's go to the right. We come down on our step here, getting a little vertical retrace here, coming up into some chroma and some horizontal information that's off to the right. So it's really kind of neat. You don't lose sight of where you're at on your complex waveform. You get to zero in on what you want to see down below. If I turn my, my B time base again to the right, I expand B even more on the bottom. If I decrease it, the inverse happens. So that's the purpose of the B time base and the delay mode. This happens to be what's called the auto mode. I have my time base switch up here in auto. I'm allowing the triggering off of A to be controlled by A's trigger control, and it had the image steady, and then I used my multiplier and my time base to zero in on the portion of the waveform I was interested in. But it could go in what they call trigger mode. And let's go back out here. Put ourselves in trigger mode. That would be, if I went to the right and I'd say trigger mode channel 1. Now I put my intensified down below. And it really doesn't matter. My time multiplier down here doesn't have much effect. But what I should see is my trigger, B trigger switch up here does. And then I can go ahead and step my delay after I've adjusted my trigger to something that I've highlighted that's of interest, and I can take a look down below in the B trace and I can see what's going on down there. And when you're displaying the B trace under the A intensified, there is a dial right here called the trace separation. And what that does is it puts more of a space between channels A and B. You can move B up and down so that you give both room enough to display the complex waveforms that are being displayed. Kind of fascinating. Anyway, the B delay is working fine. The trigger delay is working fine. Trace separation is fine. We're in good shape. And that ends our little demo of the delayed sweep. Okay, what we're going to do next is we're going to check the DC linearity and response of the Hitachi V-1050F. And we are connected right now via a probe. We're in the ×10 position, and that probe is connected to a Fluke 343A DC voltage source. We're going to get some precision DC voltages out of the Fluke. And the reason we're using the probe, we're in the ×10 position, and that will allow us to use a voltage 10 times greater than what actually goes to the scope, which will help us reduce the amount of noise that we get along with it. So we'll get a much sharper signal. And right now we are on channel A. We are in the 5 millivolt per division scale. So we're all the way clockwise, and that's our most sensitive scale for channel A. What we're going to do is, if we have 5 millivolts per division, then I would normally, if I was connected 1-to-1, I would go to the millivolt scale and I would dial in maybe 5 Or I could go to the next step and go 10 at a time, and that would give us 2 divisions. But since we're divided by 10, we actually go up another step. So in this case, I'm going to go 1/10 of a volt, which is going to give us, divided by 10 would be 0.01, 10/100ths of a volt. And we should see ourselves respond with two divisions. And we got to put ourselves on DC. And there we go. We're up 2 divisions right on the nose. And let's go one more step. And we see that we're up 4 divisions right on the nose. And yes, I could go in between 2, 3, 4, 5. There's 1 division. 1, 2, 3, 4, 5. There's 2 divisions. So I could go in fractions of a division as well. Let's go ahead and go to the 10 millivolts per division step. All right. Adjusted my triggering just a little bit there. And in this case, we should go up 1 division at a time, applying 0.01 volts. From the flue could be 0.1 volts. So here's 1. There's up 1 division. 2 divisions. 3, 4. Okay, let's go to 20 millivolts per division. And now we should go up 1/2 a division at a step. We're applying 0.1 volts, which would be 0.01. We're going up 1/2 a division at a step. Here we go. There's 1/2. There's 1. 3/2, 2. 5/2, 3. 7/2, 4. Okay. Go to 50 millivolts per division, and I'm going to apply a volt at a time now, which would be actually 0.1 volts, which should take us up, as far as the scope is concerned, 0.1 volts. So that'll take us up 2 divisions. So let's see. There's 2, and there's 4. No problem. Okay, let's go 1 volt per division. That'll be 0.1 volts per division. And if I go up should be 1/2 of this. There's 1, okay, 0.1 volts, that's 1 step, 0.2 is 2 steps, 3 steps, 0.4 is 4 steps. And let's go to 0.2, now we go up 1/2 a division at a time. There's 1/2, 1 step, 3/2, 2 step, 5/2, 3 step, 7/2, 4 steps. 4 divisions, that's what I meant. Okay, we go to 0.5 volts per division, and at this point I'm going to switch my probe to ×1, and now I should jump, if I go a volt at a time, I should go up 2 steps, 2 divisions at a time. Here we go, here's 1, 2. Okay. 1 volt per division, we'll go 1 step at a time. There's 1 division, 2 divisions, 3 divisions, 4 divisions. There's 2 volts per division, we should go up 1/2 at a time. There's 1/2, 1 division, 3/2, 2 divisions, 5 halves, 3 divisions, 7 halves, 4 divisions. No problem. And finally, 5 volts per division. In this case, if I go up one step at a time, I should see, I'll actually have to go 5 volts to get a whole division. So here's 1 volt, there's a fifth of a step, fifth of the division, 2/5 of the division, 3 4/5 of the division, 5, there's a full division. 6, 7, 8, 9, 10, there's 2 divisions. So we're doing fine. Okay, let's go to channel B or channel 2 and see how we're doing there. We're going to change back to times 10. Okay. And we're going to be on our most sensitive scale. Let's zero ourselves up here. Okay, that's 0 right there. And let's apply we should go up 2 divisions here. Okay, that's applying 0.1 volts out of my fluke. That'll be 0.01 volts or 10 millivolts going into the scope. There's 20 into the scope, and we're up 4. So that's correct. Let's go ahead and go to the 10 millivolts per division, and we go up. In this case, we should go up one step at a time. 1 division, 1 division, 2 divisions, 3 divisions, 4 divisions. No problem. Okay, let's go to 20 millivolts per division. And we should go up a half a division at a time. So here's half, 1 division, 3 halves, 2 divisions, 5 halves, 3 divisions, 7 halves, 8 divisions. No problem. Okay, we're on 50 millivolts. Adjusting my 0 again here. Right there. Okay, and whoop. All right. We are on 50 millivolts per division, and we're going to come up. We're going to apply 1 volt out of the fluke, which would be divided by 10. Would be 0.5 volts. Yeah, that's too much. 50, is that right? That's right. Okay, we're on 50 millivolts per division. We're going to apply 100 millivolts to the scope, which would be 1 volt from my fluke divided by 10, so here we go up 2 divisions, which would be right, and then 2 volts would be 4 divisions. Okay. 0.1 volt per division. Should go up 1 division at a time. Here's 1, 2, 3, 4. Okay. Here's 0.2 volts per division. We're going to go up a half a step at a time. 1 half, 1 division. 3 halves, 2 divisions. 5 halves, 3 divisions. 7 halves, 8 divisions. Right on the money. Okay. 0.5 volts per division. And I think at this point we will go ahead and switch our probe. Divide by 1. And at this point I should jump up 2 divisions as I apply a volt. There's 2. 2 volts is 4. Okay. 1 volt per division. I should go up 1 division with every step. 1, 2, 3, 4 volts. Okay. 2 volts per division. I should go up a half a step at a time. Half. 1 step. It's 1 division, 2 volts. There's 3 halves. 2 divisions. That's 4 volts. 5 halves. 3 divisions. That's 6 volts. 7 halves and 8 divisions is 4 volts. I said that wrong. Okay, that's 4 divisions, that'd be 8 volts. Okay. 5 volts per division. And we should see ourselves go up a fifth of a division at a time. There's 1, 2, 3, 4, 1 division. 1, 2, 3, 4, 2 divisions. Right on the money. So both channels are working equally fine for DC. They're very linear across the entire voltage per division range. So we're going to move on to look at AC now. Okay, well right now we're going to start our bandwidth test. And the way we're going to do this, we're feeding in a 1 megahertz signal on channel 1 right now. We've got the scope and the amplitude adjusted such that the scope is displaying 4 divisions up and down. So with 4 units up and down, a 3 dB decrease would provide an amplitude of 2.8 units up and down. And that would correspond to a 3 dB loss over the 4 unit amplitude. So what we're going to do is, right now we've got this thing adjusted. We're going to verify the amplitude on our spectrum analyzer. And then we're going to raise the frequency up to 120 megahertz, right around in there. And we're going to verify that the amplitude at that point is the same, or we'll adjust it to be the same. And then we'll apply that signal to the scope and see where we are relative to the 2.8 division mark. And we'll adjust our frequency until we get that, and then we'll read our frequency, and that'll tell us our bandwidth. So that's our plan. Let's put it into effect here. First thing we got to do, we have to verify what our amplitude is. So our gauge is going to be this spectrum analyzer, and the spectrum analyzer we want to read 5 divisions. So we're reading 5 divisions right there. That's with our 1 megahertz signal. Now let's go ahead and, without removing ourselves from that spectrum generator, let's go ahead and raise our frequency up to 120. There's 127. Let's back down a little bit. This should get us in the ballpark. There's 120 right there. And we see that we've fallen in amplitude a little bit. So we're going to raise the signal strength out of the 8640B until we see ourselves hit that 5th division mark again. Right there. Okay. Now we want to reconnect ourselves up to the scope. And right now we see that we are reading a little over 2.6 divisions up and down. So we've got to back off in frequency until we see the signal strength become 2.8. So we've got to go 2/10 of a division. Let's take her down right now. Right there. So that's 2.8 up and down. And we can get a look at our signal here. And we are reading 16 megahertz. So we're 16 megahertz beyond the 100 megahertz range. Okay, so that's channel A. Let's take a look at channel B and do the same. First of all, we put ourselves on B. And we put our trigger on B, and we're going to switch to channel B right now. We're going to reduce our frequency again, back down. We're going to do exactly the same thing we did on the other. Going back down to 1 megahertz. Right there. So we're at a megahertz. Let's see what we're doing on our scope here. Reduce our gain a little bit. Okay. Okay, so there's our 1 megahertz signal, plus and minus 4 divisions, just like we had on channel 1. Let's go ahead now and check our amplitude. And our amplitude is precisely 5 divisions. Okay. Let's go ahead and raise our frequency again. Oops. Too much. Back down now. It's about 120. All right, there's 120. Our signal amplitude has decreased slightly, so we boost it up. We're exactly 5 divisions right there. And we want to disconnect ourselves and connect our scope up again. All right. Scope is connected. And we are reading just about three divisions up and down, right on the money. Let's adjust ourselves and see what we got. All right, looks like about 120.8 megahertz. So there's a little bit of a difference in the bandwidth of channel 1 and 2. Channel 2 is a little bit better performer, but we were, I think, 15 megahertz or 16 megahertz over, channel 1, and we are close to 21 megahertz over on channel 2. Both are in excess of the 100 megahertz bandwidth that's quoted, so we got overhead and we're good. That's really all we wanted. There's enough overhead there that whatever little error I might have had, you could assume is covered by. We can look at the signal here if we want to look at the signal, no problem. Okay, bandwidth, good, thank you. And as usual, our oscilloscope will be coming with a set of manuals for the Hitachi V-1050F, PDF files on a CD, and a brand new unopened set of 100 megahertz probes, 2 of them, with the tips and so on. So you'll be completely ready to explore your capabilities with your new scope if you happen to be the lucky winner. So thank you for listening, and until I see you again, bye.